Hi everybody, and welcome to today's video. Today we're going to be talking about indirect addressing. So before we begin, I just want to talk a little bit about main memory and how the address space for a program that's running is laid out. When a program runs, it's typically given a virtual address space, and what that provides for the program itself and for us as the people that write these programs is it appears to the program to be a contiguous space of memory. And so how that memory is laid out then is, you can see it's generally like this. We have the stack, the heap, and these are ranges, these are addresses, because we care about these addresses because that's where our data and our instructions are actually going to be stored. So we're going to have a range of addresses that are for the stack and a range of addresses that are for the heap. And the code. The codes are actual instructions as well as some data. And so we're going to start talking here the next video, and then throughout the rest of the semester about the stack. It's very important to understand how the stack works by the time you get through the end of the program. That's going to be one of the core things you're going to want to take away. As far as indirect addressing, though, what is indirect addressing? And really what indirect addressing is pointers, and that we're using a value to find an address that points to actual data. You can see here there's a few lines of code. We'll go through a sample program here in just a moment. But you can see that there's just a few lines of C where we have int, and that's an asterisk x. And so that's how we declare a pointer in C. And hopefully you remember that from either 250 here at Dakota State or whatever other programming background you have. This declares a pointer. And remember that with pointers, it's important to understand that the value of this variable is going to be a memory address. It's not going to reference the data directly. It's indirect, right? We're going to access the data stored by this pointer using the address that's in that variable. This next instruction is relatively straightforward. We declare a variable y, and we store the value of 5 in that location. And when we want to access that value, we can simply use y, the variable. That directly will access that memory for us. And so that's really the big difference between the two instructions here. The two declarations, the two statements here that we're looking at. In this third statement, we have the x, which is our pointer, and it's being assigned the address of y. And so this is an ampersand, and the ampersand is the address operator. That gives us the address of y. And so what we're saying is assign the address of y. What address 5 is stored at, assign that memory address to x. And then finally, we declare a new variable z, and here you can see that we use that asterisk operator again. This dereferences that pointer. So we use that in two different contexts. One, to declare something as a pointer, to declare a variable as a pointer, and then when we want to dereference that pointer. The dereferencing then gives us that value. So we can do something like dereference x plus 1, so that'll give us the value of 5, because x, remember we assigned in this statement, we told x to point at the address that y was assigned. So this gives us the value of 5 plus 1. And so the end of, after all these four statements here, would be that z has a value of 6. Okay, and here's that program. We can just run it quick just to verify that output. Okay. And I already have it compiled, so let's go ahead and run it. Now you can see I have a typo. The value of z is 6, and so the value of z, I'll fix that quick, is 6. So this printf here is just simply printing the value of z. So we can see that it worked. Well, of course, we're talking about this because we're going to need to do equivalent things in assembly. And with assembly, especially when it comes to dealing with pointers, we have a different operator that we've already used, as well as we generally see that more instructions get generated. And so when we want to dereference something, we want to dereference a memory address, we want to dereference a pointer, we use these square brackets. So we'll look at the sample program here in assembly, and what we're going to do is we're going to declare x, y, and z, and it's going to be an equivalent of these 4 lines of code, and then we'll go through how we can get that same functionality in an assembly program. Before we jump into that, I did want to just talk a little bit about, as kind of a refresher, how the address space, how we're storing address space for the value of these variables. Now we have here x, y, and z, And what these are, these labels, they're going to be given, right? So we have X is a D word, Y is a D word, and Z is a D word. And so D word, 4 bytes. And if we think about memory on a 32-bit system, then what we have generally here is memory being laid out 4 bytes wide. Let's turn it. Right, and so we said that we're going to allocate space for X, Y, and Z, each one being a D word. And so if we have our memory addresses here, we're starting on this 4-byte boundary, then we'll have 4 bytes available for X, and then 4 bytes available for Y, and then 4 bytes available for Z. And we'll see also that these addresses change as we allocate memory for them, so as we allocate space for those. All right, and so let's just pretend that our address started at 0, then our next one would start at 4, and our next one will start at Z. And that makes sense because we'd like to, the operating system likes to store things in 4-byte boundaries because of performance. And so 0, and then 4, and then 8. Okay, so let's walk through the program. Okay, I'll get some output here. Okay, so here you can see there are those variables for us, X, Y, and Z. And then here's our main program. And we have tried to break things up into kind of somewhat related chunks here as we move through this first dump registers. Right, this first dump registers then is going to give us essentially this equivalent program here. And we can actually print that value when we're all done. I didn't even think about that, but we can move into EAX the value of Z, and then we can call printing. So we'll go ahead and do that as well, just to make sure that we get something pretty similar here. Okay, you can see let's call it print new line as well. Okay, there we go. So there's our value 6. Okay, so what's happening? Well, the first thing that we're doing is you can see that we're moving the value 5 into Y. And so these values right now, when this program runs, these are pointing to 4 bytes, 4 bytes, and 4 bytes in memory. These are pointers to these locations in memory. And so if we do not dereference them, then what those values are actually memory addresses. And in this case, because we want to store the value of 5 at the location that Y points to, then we want to dereference that value. And you can see that with these square brackets, that's what's happening. We're telling 5 to move into that location in which Y points to. Okay, so that's that first statement. And that's like the essentially the equivalent of saying int Y equals 5, or I guess probably Y equals 5. Right, the other thing that you'll notice is that we prefix that with, or I prefix that with a D word. And we've talked about this previously, in that we're dereferencing this location to move data in. We need to make sure that we move the appropriate amount of data. All right, Y is a D word, right? So we know we have 4 bytes of storage. We have 4 bytes of memory available for that location, and so this is just ensuring that we're being explicit. We're saying that whatever value we're moving in here is no more than a D word, because that's all we have. If we tried to move more into that location, then we could overwrite memory for other variables and cause the program to crash or some unexpected behavior. So we do that in order to make sure that we have declared this as a D word, we're moving no more than a D word's amount of data into that location. Okay, the next thing that we do is we move Y into EAX. And so this is moving the memory address. Let's think of Y as a pointer. So the value of a pointer is a memory address. So this is moving that memory address into EAX. And then we move the value of EAX, so that memory address of Y, into the location that X points to. Right? So we dereference our X pointer and we move that memory address into that location. And so this next 2 statements here, these next 2 instructions here, this is like getting the address, so using the address operator on Y, and then assigning that value to X. So it's equivalent to those 2 statements. Okay, so if we look at our original program, that gets us through more or less those first 3 lines. All right, so the last thing that we have to look at then is this last statement here, this last instruction. So z equals the dereference of x plus 1. That's essentially what these 3 instructions are doing. And there's a couple different ways we'll look at in order to figure out how to do this. So what do we have going on right now? Well, we have dereferencing of EAX and moving that into EAX. Well, we have to look back at what EAX was. And if we look at EAX, we can see that the last thing we moved into there was Y. So the address, the location that Y points to. So we dereference that, that puts the value into EAX. So in this case, Y is equal to 5. That moves 5 into EAX. That allows us to increment EAX and then move EAX into the location that Z points to. So we dereference Z. Now Z equals the dereference value of X, so 5 plus 1. All right, so after these instructions, we have in Z the value of 6. And we'll go through this in just a moment here. This is just simply printing the values so that we can see those examples, and then finally the print here, right? And so that's why we can see this 6 in our output. Another way we could do this, right? So this worked out because we already have that address in EAX. But we can also look at doing it this way because that kind of ignored X altogether. We didn't really need that. We didn't really need X in that particular example. So what we could do is we could move into EAX the value of X, right? We can dereference what X points to and move that into EAX. And what happens if we do that? Well, when we run a program, we can find out. All right, we get some value like this, something that doesn't really look like it makes a whole lot of sense, because it doesn't, right? The first thing that we did is we dereferenced X, right? X is a pointer, and so now that's pointing to its value. In this case, what did we put into X? Well, we put the memory address of Y into X. And so in order to get the actual data, we have to dereference again. And so now we could say move into EAX, the dereferenced value of EAX, and then we can increment. Because what we were doing is we were incrementing on the address instead of incrementing on the actual value. So now if we run our program, we can see that we've corrected that mistake, and now we get a value of 6. Okay, so there's a couple different ways to do that. But if you move that value into that variable, so now we're actually using a pointer. You may need to make sure that you're dereferencing it the appropriate number of times, right? Dereference once to get the value that that variable points to. If it's a pointer, then we got to dereference it again to actually get that data, which is the example that we did here. Okay, these next few instructions then, this is just simply moving data into registers so we can take a look at what's there. So we're going to dereference ZX and Y and move it into EBX, ECX, and EDX. And here you can see on the output, EBX, ECX, and EDX. And we more or less, for EBX and EDX, we should, the values we expect, right? So EBX in this case is our Z variable, which is 6. And we expected that value. EDX is Y, and we initially assigned the value of 5 to Y, and we can see that output there, and that looks good. And then we move we dereference the value of X and move that into ECX. And what we see here is 8049A9C, and that's the memory address. Because remember that X is a pointer, and so the value that that's going to point to is a memory address, which is why we needed in that previous example, we needed to further dereference that value in order to get the data that it points to. Additionally, I moved into ESI, EDI, and EBP, X, Y, and Z. And if we look at those values, you'll see along here, and then this is the reason I moved them into those registers, so that these would more or less kind of fall in line with each other here, based off of the dump registers function. You can see that those are all addresses, right? Additionally, what you'll notice with those is that they're all in order. And so, think back to that diagram we talked about earlier. Addresses are assigned sequentially, and in this case, because we define D words, they're defined in 4-byte increments. Our address is at 9.8 and then 9C. So if we add 4 hex to 9.8, we get 9C, and then A0. So if we add 4 hex to that, then we get that value as well, A0. So they increment. So those are in order for us. All right, so that's just the program there, and that'll be uploaded to the code folder. We also have the moving smaller amounts of data. So what happens when we move data around? And again, we've talked a little bit about this, but I think it's just important to go through another example. So if we had, in this example here, and I have a slight typo, I meant to fix that, and I overlooked it. This should be EAX. Right? And so we really just went through this. What if we move the value of A into EAX? And so I have in this program here, I'm going to go ahead and shrink that one. There's A. I defined it as a D word. It has the value of hex 00AA BBCC. And all right, so what we can do now is we can move the value of A into EAX and then dump a register. So just like we saw previously, we're moving the address that A points to. So what we're going to see when we run this program is that in EAX, we're going to have what looks like an address. It's going to look very similar to those values that moved into those registers previously, because it is. It's an address. It's the same thing. What happens though if we want to move data? So let's say that we say we want to move into BX and dereference A. Well, remember, A is a D word. A is 4 bytes. BX is the lower 16 bits of that register. So we're moving 4 bytes into a space where we only have 2 bytes. So what is the output? What is the result of doing that? Well, we're going to move into this register, dump the registers, and see what happens. Okay, and there's the results, CCBB. Right, we have to remember Indianness. Keep in mind Indianness, because what we're doing, we store the least significant bytes first. And so if we look at, let's say that we draw kind of a memory diagram as we've been doing throughout the semester, and we break this into 4 bytes, then we store the least significant bytes first. So we have CC BBAA 00. And so when I say move 2 bytes, move into AX, it starts with this value right here. It starts at this address, because this right now, this is where A is pointing to, this address. So it's going to move CC and BB, and it's going to stop. And that's why that when we look at the output here, we see BB and CC. Okay, and that would continue. So let's go back to our program here, and now let's move into CL. That dereferenced A. Okay? We're moving now 8 bits or 1 byte, and so we'll look in the CL register. Run the correct command first, and we'll see that we move CC. Okay. All right. We have a difference though, and again, this should be a little bit of a review because we talked about this previously. We have a, in that example, we declared that D word with that value. Right? Now, when we declare, like in this example B, we say that I'm going to declare 3 bytes, but I'm going to do them individually. I'm going to do them separated by a comma. That changes because with that byte value, remember, the Indianness only affects multi-byte. When we store these as single bytes, then we don't have necessarily the same problem, and we're not really dealing with Indianness. So now if we have our data being represented here, okay, and we have our 4 bytes, what we'll do in this example is we'll define, so this will store AA, this will be BB, this will be CC, and this will be BD. All right, so now, if, as in this example right here, let's say that we move into BL, and we dereference, or into DL, I'm sorry, and we dereference B. What happens? What value are we going to get there? AA, because that's what was stored first. We're not dealing with Indianness because it's only a single byte. So again, it can take a little bit just to get all this memory stuff straight, and so definitely go through these examples, go through the code, move data around, and work with some pointers and the dereferencing here just to make sure that you're continuing to understand what we're going through. Reserving space is another section. We really haven't used it a whole lot, although some of you probably have decided to on your own. That's the BSS section. And if we look at in our program, we have segment.bss. What we can do that is we can use that section to reserve space for uninitialized data. So we have these instructions, res B, res W, res D, byte, word, double word, and we can optionally put we put a prefix or a label in front of that, and then the number of bytes that we want to reserve. So I could say data reserve byte 100, and that would give me 100 bytes of memory that is pointed to by this label, this variable data. Let's see, we'll just go through an example here, more like this one here. Okay, so here I call this buffer, and I reserved 100 bytes for buff, and later on in this program, I'm going to use gets. So if we want to call an external function here, extern, and then the name of that function, so just like the printf example, very similar to the printf example that we went through previously. What I'm going to do though is I'm going to use that value in order to get something from standard in, to get input from standard in. Now, normally this would be a very, very bad idea, because what we're doing is we're calling functions, or we're calling string functions from the command line, and then we're moving that data unrestricted, uncontrolled into a buffer. This is a classic buffer overflow example, and I'm going to plan on going through that later this semester. So if you're not quite sure exactly what the damage can be from that, we'll probably get through that later on. If not, we cover that in 444, and so we'll definitely be doing some limited exploitation in that reverse engineering course. So let's just go through these instructions here, and a better activity. What we're going to do is I'm going to move the buffer into EAX. So I'm going to move that address into EAX, push EAX, and then call gets. And so this function expects the address to a buffer, an address to a char array before it's called. So that's setting that up there. That calls gets, and you can see right now the program is waiting for me to enter something into the command line. So I can just enter my name. And then after that call, this cleans up the stack. And again, we'll talk about that here in the next video. I move that address for buff into EAX and then call print string print new line. So all this is going to do is simply take whatever the user typed in and echo it back to the terminal here. And there we can see that's what happened. So what this is beneficial for, and why you might choose to use the BSS section versus the data section, is that this will give us 100 bytes of memory when the program runs, but we don't have to initialize a value. Because if we're just going to simply overwrite it, like in this case, we're going to run the program and we're immediately going to overwrite the memory that was pointed to by this buffer, then it really doesn't serve a purpose or a point for us to initialize that with data. So that's an example there. Let's see, I think that's everything for today. So again, I'll get all the code posted. I encourage you to go through that, and if you have any questions on anything we covered, let me know. Next topic, we'll be moving into the stack. So I'll talk to you in that video. Thanks.